Hello everyone, welcome to the next session on ANSYS Workbench tutorials. In this session, we are going to analyze the exhaust valve whose design we have created in the previous class by using steady state thermal analysis. We want to check the heat transfer that takes place over an exhaust valve. As you know, exhaust valves are generally subjected to a very high temperature. So it is important to analyze the material and its temperature distribution when it is subjected to a particular ambient temperature such that we know what would be the heat distribution over it. The exhaust valves are primarily made of high heat resistant metals such as nichrome, silicon chromium or cobalt chromium alloys. For this analysis, I am choosing cobalt chromium alloy as the material. You can alternately study about nichrome or silicon chromium as the material and analyze your valve. So we will start by double clicking on steady state thermal. We'll first go to engineering data and add material over here. This cobalt chromium alloy. The property that I need to give to define this material is the isotropic thermal conductivity. So I will take you to a website. I'll give you the link to this website. I'm using this website to get the details of cobalt chromium alloy. These are the various properties as you can see on the screen. The compound formula COCr, the molecular weight, appearance, melting point is given. Melting point value is 1330 degrees Celsius, which means it can bear this temperature before it melts and decays. So we can subject it to this high temperature. Now the temperature with which the exhaust valves generally come in contact could be a gas of 350 to 400 to 500 degrees Celsius maximum. So this is actually quite high. So your valve will have a better life and it will show better performances. Now what property we need is the thermal conductivity. As you can see here, the value is 9.4 watt per meter Kelvin. So I will substitute the value here, 9.4. The unit here is watt per meter degree Celsius. Now whether you write watt per meter degree Celsius or watt per meter Kelvin, it is both the same. The temperature that I'm going to use here is 22 degrees Celsius. That is the normal temperature at which these values are generally given. Or I would say that this is the standard temperature according to the American standards. This is what I have taken. Next, I'll go to project and update project. Next, I'll go to geometry and right click. Since I have already created the geometry in the previous class, I will directly import the geometry. Next, I'll go to model and double click on it. We had created this geometry in the previous class. I will go to geometry and I will first assign the material cobalt chromium alloy. Next, I'll go to mesh and I'll change the sizing from coarse to fine and update. Next, I'll go to steady state thermal and right click and insert temperature. So this end is generally exposed to the temperature. So I'll give a temperature of say 400 degrees Celsius. Now I will apply convection on these outer surfaces. So I'll press Ctrl and select these surfaces. Right click and insert convection on these 7 faces. Now here you can give a value of coefficient. The value of film coefficient for ambient air is generally zero point 0.5 to 1000 watt per meter square degree Celsius. I am giving a random value of say 3.2. Next we will go to solution and insert thermal temperature. I will next insert total heat flux, and also if you want to see the directional heat flux you can go for it. I'll go to solution and solve. We'll first check the result for temperature. You can see here the maximum temperature is at this area, and here you can see a steady decrease in temperature. Now I'm saying steady because we are doing a steady state thermal analysis and this is not time bound. So these are the values of temperature over this body. Corresponding to the color, you can see the value here. In case you want to find the temperature at a particular point, you can just click on probe and select that particular point where you want to find this temperature. You can see the location of X, Y and Z over here in the results below. Next we'll go for total heat flux. You can see the value of maximum heat flux over the body is 1.8564 into 10 raised to 5 watt per meter square, and it is at this zone. If you want to find its value, just click on max min. You'll figure out as to where the heat flux is more. So you can see here the minimum value of heat flux is 544.54 watt per meter square, that is in these blue zones. Next we will see the directional heat flux. I'll just click on max min again if I don't want to see it, or if you want to see you can click on max and min. The maximum value of directional heat flux, it is showing along the x-axis 1.112 into 10 raised to 5 watt per meter square, and the minimum value is also given. Now if you want to find the directional heat flux along the y-axis, you can check that by changing this to y-axis and solve once again. So you can find the directional heat flux along the y-axis. The maximum value is 1.5877 into 10 raised to 5 watt per meter square. So this is how you can solve. Now I'll show you one more option. Suppose if you go to convection and you do not want to give this value of film coefficient, you can click over here. And when you come through this arrow, you will see that you have given a constant value. That is why this option constant has been ticked. Now there are two other ways of giving convection coefficient. So I will go to tabular form. For that, you can just import temperature dependent. Since it is not transient, we are not going for time dependent. We are going for temperature dependent. So from here you can choose the value. Now I have already solved one analysis wherein I have shown you the use of this option, the first one. Now I'm not using the first option here. I'm using this one, stagnant air, vertical plane. Okay, so that's the plane in which I want to calculate the convection. So this is how I have chosen. So if you see here, a table appears with certain temperature and the convection coefficient in watt per meter square degree Celsius. So as per the temperature, you're going to get the convection coefficient being changed. So this is another way wherein your convection coefficient has a relation with temperature. Whatever is the temperature, accordingly your convection coefficient is going to work. So I will go to solution again and solve. So we'll check the temperature now. The maximum value is 400 and the minimum is 153. Previously it was 191. So you can definitely see a temperature difference again. If you want, you can animate and check the heat transfer over this body. or it's actually showing your temperature variation over this body. So you can just click on animation. Now when you click on heat flux, you will see that the total heat flux is 2.309 into 10 raised to 5 watt per meter square, and the minimum value is 568.75. For this also you can animate and see the result. You would see the animation is mainly working in this zone because that's where you can see a temperature difference. Next, you can see the directional heat flux along the x-axis. These are the values for it. And this is the directional heat flux along the y-axis. Maximum value being 1.97 into 10 raised to 5 watt per meter square. So this is another way of giving convection coefficient in case you're not sure as to what could be the ambient temperature. So based on the temperature of the body, your convection coefficient is going to be decided, and accordingly you will find the heat transfer over the body, or what is the temperature distribution that has happened, or how much heat is lost in which section over the body. So with this I end the session. I hope you have understood how to analyze an exhaust valve with cobalt chromium alloy as the material. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.